Welcome, everybody. So I'm going to follow up a little bit on what Ian has talked about. So this is the topic that I'm covering here is what happens after we've identified the stretch of data that's interesting and that's worth looking at in a lot more depth. Which means that on the one hand, I can afford to spend a lot more time and computer power onto that stretch of data because Ian has already done the hard work in telling me exactly where to look. On the other hand, you will see that a lot of the tools are very much the same. The statistics, the models that we use are very, very similar to the point where, in effect, the lines between what Ian works and what I work on is actually very, very blurry, and we both use pretty much the same techniques. And you'll find there is a lot of overlap. So the story of this is how we go from this stretch of data. This is a plot that you've seen in different graphs forms from Alan and from some of the other presenters. So the strain out of the detectors on the Hanford detector and the Livingston detector at the time of 15914, but this is the unfiltered, unalterated data as it comes through, and it's very hard to see what comes out. What I'm going to talk about is how you go from there to something like this, which is a probability density functions, which measures for some parameters, here for instance the masses of the two black holes, M2 and M1 here, the probability that they have any specific value. Sorry, there is a very strong echo around here. Is that, am I the only one hearing it?
Yeah. It's the acoustics in that corner.
Okay. Sorry, I can hear the sound of my own voice, and that's just not nice at all. Yeah, so we get those masses estimates. Part of the point and why we often say that gravitational wave astronomy and gravitational wave astrophysics is a statistical science is because if you just get those two numbers there, that's not really the answer. The real answer includes the uncertainties, and without those uncertainties, you're not really measuring anything. And we spend most of our time making sure that we understand our uncertainties, which is why, and I'll go into a little more details, why those uncertainties have actually this extra fancy air on the uncertainties themselves, because we take our uncertainties very seriously. We also like to do probability density functions like this, those one-dimensional ones. We like to plot them in 2D actually, so this is the two-dimensional probability density functions. If you just project all of the probability volume here onto this axis, you would find the same one-dimensional one. We like to do the 2D one because we can claim we're much better in 2D than in 1D. The correlations in the parameter space are such that actually we don't measure M1 and M2 individually very, very well. That's not what the type of signal that it gets imprinted. So going back from that, that type of graph, we actually, as you've seen before, we do tend to take a look at the data a little more in slightly different ways. This is the same data as before, but filtered in a way that actually changes the units. If you notice, this is this whitening process that we talked about, which does make the signal a lot more apparent. And you've seen those type of spectrograms where we can already see after having when you know what you're looking for, you can see and you can do this type of treatment and you can see the signal. But from this type of data, from this type of somewhat treated and pre-treated data, the single theorem by which we do almost everything of what follows is this one, which I presume most of you know about. Most of the gravitational wave scientists in the audience have seen ad nauseum. But this is basically what we do. So in red is the quantity that we're going to be looking for. That's this posterior quantity. That's a measure of the probability of the lambda parameters, which can be the masses, the distance, the scale location, any set of parameters. This is the vector of any parameters that you're interested in. What is the probability for those parameters to have a specific value, given that we've just observed some data and that we have a model of the for the signal? So the first ingredient of this theorem is the model. And we have to be careful when we say the model, we often use that as a shorthand to mean the signal model, because it's the one that is that makes for very beautiful plots and that has those fantastic movies that you saw this morning about the two black holes in space orbiting, etc. But really, when we say model, we also mean a model for the behavior of the detector, a model for the noise, whether it's stationary, by how much, and what type of Gaussianity, what is this power spectral density, and all of this. This is a model that really tries to reproduce everything the detector sees, both the noise and the signal. Next, going to more detail in the waveform model, so that part of the signal model. You've seen that plot before, so one thing I want to highlight on how we parameterize compact binary coalescences, and same warning applies to my talk as any of the other ones. I shamelessly focus on compact binary coalescences, ignoring all of the other very important sources of gravitational wave signal in the interest of time. So we divide the parameters that we measure from those CBCs in two broad families: the intrinsic ones that have to do with the intrinsic properties of the binary itself, and the extrinsic ones that have to do with the relationship between that source of gravitational waves and ourselves. So things like the distance and the sky position, everything that has to do with us is this intrinsic family. Anything that has to do with the waveform itself, masses, spins, maybe eccentricity, although, as was mentioned before, we tend to make the simplifying assumptions that eccentricity is irrelevant in our observations. That's an assumption we make for the flagship standard analysis. We do also do side analyses where we ensure that this is not crazy, and what if we saw something eccentric is still something on our mind. So looking at gravitational waveform models, let me spend a few seconds on this particular plot. So there are two, this is time in x-axis, this is data and model around the 150914 detections. Here, in this y-axis, fitting the gray plot, is in units of sigma deviations from the noise, meaning how unlikely is that particular time to be Gaussian. So at the start here, it centered around 0 and has amplitudes that are well within 1 sigma plus or minus. You can see over here, the gray is a little faint, I apologize. It starts to be much higher than 1 sigma. It starts to be a significant deviations from what Gaussian white noise would be. On top of that, I've also overplotted what is the gravitational wave model that we expect, that fits the data the best. That's the blue curve. That blue curve is in different units. That's in the strain units, meaning those very deformations of space-time that we've talked before. So this is dimensionless. This is a ratio of length. How big was delta L caused by that's deformation caused by the gravitational waves divided by the length that you're observing it with. So that's a dimensional one. When we transform one to the other, we basically are including the sensitivity of the detector in it. And so if I do the same procedure to my blue model that fits best that I did to the data, I whiten it and I get this red trace, which thankfully fits the data very, very well indeed. And this, this procedure, we like to say it takes into account the sensitivity of detectors, and you can see how at lower frequencies, where the period here is longer, the reducing factor is a lot bigger. There is much more difference between the red and the blue as there is at much higher frequencies. And that's because the detector is less sensitive at those frequencies than it is at those frequencies. There's another visual way to see it. This also highlights one of the things that made us quite speechless when we detected that signal, 5914, the first time. It's loudest, the signal model is loudest, right where the detector is most sensitive, which there is such a thing as too good to be true, and so we were very, very suspicious the first few days. There was a lot of, head scratching about how come. Now, looking now in this strain units, so deformation of space-time, just because the curves look a lot smoother. In blue is that best fit signal. What happens if I divide the masses by 2, both masses, M1 and M2? I get something that is less strong, that the amplitude is reduced, But I also get something that goes to much higher frequency towards merger. It vibrates a lot faster. So this is something that the masses, those two effects, is something that the masses do. We tend to measure in particular chirp mass, that particular combination of masses. That's the one that governs really the frequency evolution of the signal. And to a lesser extent, the mass ratio. Those two statements are true for the in-spiral part of the signal, for that first portion of the signal where the two black holes are orbiting around each other. The last part of the signal, the ring down, that's after the final black hole product has been created. And so it's governed by the properties of that final black hole. The biggest property, the most dominant property of that final black hole is its mass. Its mass is directly related to the sum of the masses of the two black holes that went into it. And so if you see that last part, you're actually more seeing the total mass of the system than the chirp mass. And if you see both, you can try to play one against the other a little bit. I should add that this illustrates the type of correlations that we have. Distance as an effect. A gravitational wave that's further away has the same amplitude that's reduced, but doesn't have a change in frequency evolution. So while there is some correlation, some similarities, we should be in principle able to distinguish mass change as opposed to a distance change. Now for spins, if the spins are aligned with the orbital angular momentum, so here I'm putting both spins of the two black holes aligned with the orbital angular momentum, we see what we call an orbital hang-up. So the stronger the magnitude of the spins, the more it will delay, or if it's anti-aligned, more it will accelerate the time to mergers. It doesn't change the amplitude much, but it does change the frequency evolution. However, and this is the big one, if they are not aligned, and a priori there is not strong reason to believe every single one would be aligned. There's some reason to believe where they wouldn't be too anti-aligned, and we can go into the astrophysics of that, but taking an agnostic approach to it, if they are not aligned, then conservation of total angular momentum, the orbital plane will precess. That precession will induce modulation in the waveform itself, and now the red waveform, which is a highly precessing version, everything else being the same, I just added very strong precessing spin on this best fit from 15914. Now that waveform looks completely different. Sometimes it has the same amplitude, sometimes it clearly doesn't. It has somewhat a similar frequency evolution, but not quite, not all the time. And that starts to mess things up quite a bit, and all of those parameters end up being quite correlated. That's for the signal model. I'm going to go very quickly through this because you've seen much better talks about the detector noise model already. The only point I want to bring it really is that it's complicated. There is a lot of different noise sources that enter at different portions of the detector itself, from seismic vibrations, suspensions, thermal noise, the mirror coatings, which are at a finite temperature themselves, so they vibrate, and that's bad. Quantum noise, which appears at much higher frequencies, which also limits this, shot noise, radiation pressure, etc. Those are, loosely put big lines. We know there are some areas where certain sources of our noise dominates, but noise is everywhere, and we have to model this quite carefully. Otherwise, well, this is high precision stuff. You would get the wrong answer. So this was for the model. Now looking at the likelihood a little bit. This is that particular term in Bayes' theorem. I'm going to use the Bayes' theorem as a linchpin throughout this presentation, by the way. So the probability of observing a particular realization of the data, if I assume that inside of that data there are exactly those parameters and my model is correct. I'm assuming that my model is correct everywhere. I can't really do without that. What I can do is use several models and compare, but right now let's just focus on the one model. I'm assuming there is this gravitational wave in it. What's the probability that I would actually see what I'm seeing? And the way you do it is going back to this fairly odd units, those sigma deviations from the mean units. In gray is again the raw data from 15914. In red is my best fit signal as seen by the detector. So I've applied this transformation that takes into account what the detector can and cannot see. If I subtract both of them, now I see something that is, pretty centered around 0 and doesn't have a lot of deviations. I can ask, if there were no signal in the data, and my noise was Gaussian, and it was stationary, and I understand its property, what is, by random chance, the chance of the black trace appearing in my detector, in a signal-free operational detector? That's a well-defined question that I can answer because it's Gaussian noise. Technically speaking, any specific realization of the noise has a probability that's vanishingly small. So we talk about probability densities at that level. But basically, what we do is we just integrate this whole thing, and we say, well, how many sigma away from Gaussian is this? If it's not a lot, then that means that my red signal probably matched my red model matched the signal in the data very well. If it's a huge deviations from 0, then presumably I did a bad job at subtracting whatever was in it. That's the key in the likelihood. Basically, that's the how we build the likelihood. You realize by constructing the likelihood this way, what we've done is we've made very strong assumptions on Gaussianity and stationarity of the noise. I will go into some ways how we allow ourselves to deviate from that a little bit. Those are still pretty key assumptions. They make the math a lot easier. I mean, like a lot. But it's not, we expect it won't be always correct. So far, we've been okay, with one very notable exception, the binary neutron stars. But all the black holes, they are so short. Come on, it has to be stationary on those milliseconds time scale, hopefully. It's probably Gaussian, right? And we will see how it's not. So just to go into a little bit of mathematics now, because this is something that we're going to look over at the tutorial this afternoon. So when a gravitational wave hits the detector records some data. And the data is the noise of the detector itself, as the detector behavior happens. And then the signal, which has some parameters, which we don't know a priori, inside of this response function, which is how the detector reacts to certain frequencies coming from certain gravitational waves at certain frequencies coming from certain directions. All right. So taking this equation, we can do it for a particular data. I'm just labeling one. There is a particular realization of the noise, and I'm adding on it the effect of the gravitational waves. If I make some assumptions about the noise, such as Gaussianity, stationarity, and a power spectral density that I've measured before or that someone else gave me, I know what is the probability of observing that particular realization of the noise. And then it's just a matter of subtracting the response of the detector and asking whether that quantity, which I can compute because I'm picking some lambda prime parameters. I don't know whether those are the same as those ones, but I can just try a bunch of those and ask for every single one of those, is this any consistent with the probability of the noise? That function, that probability, is formally the likelihood. Technically speaking, the likelihood is a function of the residual, this subtraction between the data and the model that I tried to do. So it's a probability of the noise of that time series. But because we compute it varying the parameters that go into the model that we used to subtract, we end up thinking of it as a function of those lambda prime parameters. It's just abusing notations a little bit. It's just a lot more convenient to talk about what is the likelihood of 30 solar mass black hole in the data, as opposed to ask what is the likelihood of this particular time series, which is very long and changes all the time. So we tend to think of it as that quantity. So it is the probability of drawing that residual, but we tend to think of it as a function of that probability. So that's for one data point. I can do this for one frequency, but I can do it for many different frequency bins in my data So at every single time or at every single frequency, I can compute that quantity, and then do this joint probability of all the frequency bins around. So that's where the integral over frequency comes in, which we're going to compute this afternoon. So how we compute this probability of this residual, residual being the data minus the signal. I hope I did a good job in estimating. The noise model enters in this form. So when I say we can compute the probability of a particular noise realization, so this is N1 is the noise at frequency 1, which say 20 hertz. N2 is the noise at 21 hertz, say. And I have that probability at every single little frequency bins that I give. If I assume it's Gaussian, then by definition, that's the probability of the noise, including that little quantity here, the correlation matrix, which I can compute by assuming stationarity. If I assume stationarity, then I can compute this matrix just by using the detector power spectrum density, or the sensitivity of the detectors at a specific frequency. This is something that will become very important later. I just wanted to throw the equations in there. So, in the end, to summarize, I know I'm going, quite deep into this, but the likelihood is pretty much the only handle we have in what's in the data. Everything we see is through the likelihood. The likelihood, changing a few terms here and there, is in loose term is the exact same thing that we use for detections, that we use for parameter estimation, that we use for model selection. It's really the lenses through which we understand the data. The likelihood, whether it's a model signal like a CVC or unmodeled burst, we still use the likelihood. It's just what is M changes depending on the amount of physics you assume. But it's still all about the likelihoods. So I hope you will forgive me for spending so much time on it. So it is the probability of obtaining a particular data D, assuming that there is a signal, and assuming that the noise is stationary and Gaussian. We do this in practice. When you write the math, you assume that the discrete bins are continuous. This notation here, that's the overlap, between that residual, so that's a time series with itself. So we do this notation of parentheses, straight line down and parentheses. In the end, that's what this overlap product between two time series means. This product, which is really the fundamental multiplicative property of the space in which all of our models and time series lives, that product operation is dependent on the detector and on the detector noise, and we have to estimate that all the time. So we have this, it's not quite a vector space as it turns out, because the sum of two waveforms is not necessarily a waveform, but it is a Hilbert space with a funny product rule which changes as a function of time and how often you do the analysis. But we use some of those mathematical rules to play a lot of tricks that you will see this afternoon. So that's the likelihood. It does include the noise. In practice, though, we use something a little bit different. This is the full likelihood that we actually use in practice. So this is what you see when we describe in somewhat hand-waving terms the probability of seeing the residuals. In practice, though, we account for a lot more things. So again, the probability of observing particular data, assuming some parameters in a model. And the key here is, what are those parameters? We would like to think of it that there is only 15 or 17 parameters if you assume eccentricity. So it's the two masses, the distance, the time at which it happens, the sky position, etc. All of those physical parameters that we are interested in. There is also a lot more parameters that we have to include in these functions that we're not interested in, so-called nuisance parameters. Those parameters come into parameterizing the noise spectrum density, for instance, because we know that in practice it's not always Gaussian and stationary, But more than that, no matter what we do, we don't know what is the intrinsic noise process that creates the noise in detectors. We can only measure it and estimate it and make very educated guesses, but we don't really know. We don't have that formula in place. We know what we aimed for. That's a good basis, but it's not exactly what the detector does. So we have to estimate it. And if we estimate it, that means there is some error in the estimate of the power spectrum density itself. Luckily, to deal with those errors, we have several strategies. One of them is the standard, I should say, techniques where you average across a lot of stretches of data. So in the end, you get estimates that are fairly reliable, but that really strongly depend on the stationarity assumption. If you average over many hours of data, it's very likely that the detector's property have changed in between, and so your average now is not as useful as it could have been. Another approach that we take in parameter estimations, if the data warrants it, is to actually fit the power spectrum density, build a model for the power spectrum density, here represented by a cubic spline fit, and added a few, an a priori unknown number of Lorentzian lines to represent the lines in the PSD. Some of those lines are known, and we know exactly where they are, and we can just use that information. Others, we have a loose idea where they are, but they keep wandering around just a little bit, enough to make problem. And some of those, we just have no idea where they come from. So there is some freedom in the fit to do this parameterization. And so the parameters such as the number of Lorentzians, the location, the height of the cubic splines, and the parameters, all of those come also into those lambdas. We're not very interested in those. This is not something that we're doing to measure the PSD itself. It's something that we're doing to account for the fact that we can't measure the PSD very well. And so we marginalize over all of those extra parameters at the cost of making our uncertainty in the parameters slightly bigger. But while we pay a cost in statistical uncertainty, at least we remove some of the systematic bias from misestimating the power spectrum density, which everyone agrees is better. So the other thing is, well, here you have, so instead of writing the two parentheses with the line in the middle, I just make it as if it was a square. But I'm adding a new term here. This is a glitch model, which is specific to a specific detector. Here's the little subset N is for any specific detector: Hanford, Livingston, Virgo, Cagra, Geo. I have a glitch model which will be something that is not astrophysical of origin, that is not coherent between two detectors, and that I'm using to subtract to the data at the same time as I'm subtracting the signal. You can imagine that there might be some somewhat dangerous correlations between the parameters that describe this glitch and the parameters that I'm trying to measure inside of the noise model. Yes, they are. One has to be very careful when you subtract those glitches, not to subtract too much of the signal. But leaving them in can be pretty bad as well, as Ian was showing. So this is the example where the assumptions of Gaussian noise is just screamingly wrong. The Livingston observations of the binary neutron stars, you see Gaussian noise almost everywhere. There is this track here that's not Gaussian noise, but that's the good kind. That's the gravitational signals. And then there is that giant thing that is not Gaussian noise, but not the good kind. That's just a glitch. So we did subtract the signal with this glitch model. So we let the model fit it. We are being very careful, and we rely strongly on the fact that we have multiple detectors for which we can predict what the gravitational signal should look in all of them, but glitches should only matter for one of them. So any type of glitch power that ends up subtracting coherently between the two, that's something we veto, and we try to make sure the signal doesn't do. So in the end, our model for the data, if you will, in this picture is the noise, the response of the detector to a signal, plus some glitch, which also has an unknown number. So by the way, now our lambda parameter, it's not just 15 or 17 numbers, is the numbers of numbers inside of that list of numbers is an a priori unknown number. It's a lot of fun. It's, the bookkeeping is a bit of a nightmare, but it's a lot of fun. So moving forward, there is also that response function of the detector. Well, it turns out it's also a function of frequency and parameters as well. It can be parameterized because measuring that response functions, that's the whole idea behind the calibration that Alan talked about. We don't know it exactly. And anything that we don't know, we model and marginalize over because we do not want any bias. We don't want to make the wrong conclusion from it. I mean, some of the scientific goals that we have with gravitational astronomy are very ambitious, like proving that deviations of general relativity, for instance, just to name, one. That has such a huge burden of proof. I mean, GR is doing pretty well. So to really, if you are convinced that there is something wrong with GR and you have a gravitational wave in the data that doesn't match GR, you will have to convince a lot of very skeptical colleagues that you actually understood what the data was and that you didn't forget that there was this photodiode saturating in the 76 chambers on that optical table somewhere. In particular, we calibrate our detector, so to go from photon count to actually gravitational strain, that calibration procedures has errors. You wouldn't want to claim GI is wrong just because you didn't take into account the fact that we cannot know exactly, very precisely, what the calibration is. So this is the type of models that we have. This is in amplitude, in percent, amplitude and in phase. The calibration value, best fit value that we have for the calibration model, and some 1 sigma uncertainty around that value, which we measure. There are some, as a function of frequency, there are some ranges in frequencies that are much better measured than others. The people who do the very hard work of calibrating detectors naturally focus at getting it more accurate in the range of frequencies where the detector is more sensitive, where it matters most. But then we marginalize over those uncertainties. So our actual signal that we're trying to fit to the data, instead of being just the signal model predicted by our waveform model, we actually multiply it by some fraction of amplitude and some dephasing. And we marginalize those we use those probabilities to, in the giant likelihood equations, we use those parameters, we sample over those parameters, and we marginalize, we integrate over all the possible values using a prior on those values that's given by those type of graphs to take into account the fact that even the calibration of the detector is not certain. Next is the prior. So everything else that I've said so far is very difficult, I think, but we have an idea what to do. This one is a little simpler, but we have no idea what to do. So some of the parameters are fairly straightforward, right? The cosmic censorship is a good place to start. Let's assume there is nothing special about where we are in the universe, and a priori gravitational waves can come from anywhere uniform in co-moving volume, which means it tapers off at very high redshifts, but that's actually going to be a problem, because if it tapers off a high redshift, that means I have to assume a cosmology, but I don't know H0 exactly. So what do I use? And very reasonable people disagree as to what I should use. So that's one we thought was going to be simple, but turns out isn't. Uniform in the sky is a little more simple, unless you start talking to people who claim that, oops, I'm sorry. Unless you talk to people who do galaxy catalogs and who will claim that certain black holes have to come from certain galaxies and the one that are nearby starts to matter, and so it shouldn't be uniform in the sky. But right now we're being saved by the fact that those galaxy catalogs are not very complete up to the distance at which we're sensitive, so we're just saying, yeah, it's got to be uniform. But really, no, but there's only so much we can do. There is a lot of parameters for which we don't really know. Masses is one of the main ones. So a priori in the universe, small things are more likely than big things. It seems to be a bit of a trend. Usually it's a power law of certain index, which you could put in as a parameters on your prior and fit. That's how you do this type of a population inference, and we do that as well. But really, we don't know. We're trying to measure. We have 10 black holes, 1 binary neutron star, it's not a great number of statistics, so any type such measurements will be dominated by what prior you put on the index of the power law that you use as a prior. So you have a prior on your prior parameters, and it's priors all the way down, pretty much. The thing is, all of those things do matter. Like the answer you will get out will be different depending on which prior you use. And some people will argue that, yeah, it should be flat in masses, obviously, because you don't know any better. Yeah, but I measure chop mass and mass ratio a lot better. So do I do flat in chop mass and mass ratio instead? Because those two are not the same prior at all. There is no, as far as I know, I would be happy to be proven wrong, because then it would be one of the last bullet points I have to care about I could remove. There is no good answer. So what we do right now in all of the results we've published, we try to do two things. First, unless there is some strong astrophysical evidence, we do flat priors on the parameters that are of most interest to the astrophysical community. It's more, astrophysical community has, as far as we can measure it, more interest in the masses of a black hole than the chop mass of a particular binary. Even though we would rather report the chop mass because we're much better. I mean, the accuracies on this is just unbelievable. But instead, we report the masses. And so we do a flat prior so that people can look at those masses estimates and not have to, in their mind, remove a prior. The other thing that we do is that we make sure that we have enough samples so that anyone who downloads our samples afterwards can just reweight with whatever procedures they want to have whatever prior they want. So we try to make that prior to be somewhat close to what is the overall prior consideration that most people would have. So for distance, for instance, we would try to pick a particular value of h0 that is not too far off, but we're not going to do a log in distance, which would make it, which is actually Jeffrey's prior, but that's a technical detail I can go later. But that would be impossible to reweight. So we try to be somewhat reasonable to allow for more flexible analysis down the line. We're not claiming that our prior choice is the true a priori probabilities for all of those parameters, because I don't think we can write that. The last argument, the last ingredients of this all procedures that I'm not going to go into detail now, because you will do it this afternoon, is there are a lot of parameters in there. They all can have a lot of values. You need to compute that number a lot of times before you can get those curves. It's high dimensional. It requires quite fancy sampling algorithms. In particular, every time you compute this, you need to compute a new waveforms, and a new model, and a new calibration realization, etc. That can actually be quite slow, depending on how much physics you want to do. But that's the reward. At the end, you get to make plots like this. So this is the M1, M2, just because it's one of the top parameters. And if I try to put all 17 in them, you can't see anything. So for all of the detections to date, you can see our tiny little neutron star here. I will leave you with this. One thing that you can see here is the black holes that have a lower mass, meaning that they merge at much higher frequency, we tend to only see the in-spiral part of that signal, right? Because the merger is at such high frequencies that the detector is not that sensitive. Since we can only see, or almost only see, the in-spiral part, we measure the chop mass much better than any other combination of masses. So for those low mass black holes, on this graph of M1, M2, if I make curves of constant chop mass, they will have that curved shape that follows all of those PDFs. That's why all of those are curved like this. By the way, this one there is also curved like this. The thickness of that line is 4 orders of magnitude smaller than the pixel size on that plot. I just can't plot it. We measure the chop mass 4 orders of magnitude better than anything else. So this one is very, very thin line. But all of the others, you can still see the trend and the correlations, and you understand why it's kind of frustrating to have to admit that our uncertainty in M1 is like that big, while actually we measure something a lot better. I mean, it's not like we have a giant rectangle of that shape. We have a clear track in it. On the other hand, black holes are much heavier, so that the ring down is within the visible band, the ring down being dominated by total mass as a mass property. There we can constrain total mass. And so lines of total mass, M1 plus M2, are just the diagonals, and that's where you can you can see how that curve starts to shape differently at higher masses because we can see different parts of the signal. There is a golden spot, our lovely 5914, where actually we can see kind of both. So we have a much higher constraints that we would have otherwise everything else being the same. But you can still see that trend for all the signals. While that type of correlation consideration gives you the shape of those probability density functions, the size of which is to zeroth order just how loud the signal is in the data. That's just signal to noise ratio. And that's all I have. This is a picture of beautiful Livingston in the swamp of Louisiana, which has nice forests which they keep cutting, and it makes a lot of noise on the ground when the trees hit.